this operation is not allowed in the first place, right? And the result will be the number of rows for A, okay, from A, and the number of columns from B or C. Okay, so basically, the size must match, no matter you are talking about the left-hand side or right-hand side. So it's the size is not an issue. Okay, so we can look at like element, if they match or not. So this one, okay, according to the definition, okay, B plus C will be the corresponding element, add together, and the multiplication will be AIK times BKJ. Actually, like this. The result B plus C, the KJ. I mean, the result B plus C will be BKJ plus CKJ, and this we run through all the case, and then this becomes all numbers, so we can apply distributive law like this. So once we have this, okay, obviously this one, according to the property, will become this one. And the second term, according to the definition, will be this one. Okay, and then we can write that back to be this one. So we have the case, okay, to prove this part. Okay. You should be able to write something like this, okay, for every property. Okay, not just this one. And you need to remember, the measure multiplication is not commutative. Okay, so for example, like AB and BA are not equal. Okay, this is the case. Okay, A is this one. Okay, B is this one. Okay, if you look at this example, okay, obviously because both of the measures are of size 2 by 2, so you are able to change the order, okay, of the multiplication. At least you could do that. But will the results be the same? You have to check. Okay, I mean sometimes they are the same. I'm not saying they are different all the time. Okay, but you have to check. Okay, so for example, the first one, okay, 1, 3, 2, 0. So so the first one, 1, 3, 2, 0 is 2, right? And then the second, 2, negative 1, 2, 0, so it's 4. And then 1, 3, negative 1, 2, so it's negative 1 plus 6, so it's 5. Not very clear. And 2, negative 1 times negative 1, 2, so it will be negative 4. I'm sorry that this is like a result A times B. How about B times A? What's the result? 2, negative 1 times 1, 2. So it's like 2 minus 2. So it's 0. So you actually do not need to finish that. You know immediately that these two will not be the same, right? Okay, of course you could finish like American, but just want you to understand, like they are different. Okay, you can finish up the B times A and to get a field. And one more thing, okay, because in matrix, okay, the cancellation is not always valid, okay. It's not, sometimes it's valid, sometimes it's not. But we will talk about when it will become valid later on, okay, later on. So here is the case. AC happens to be the BC, this one, times C, 1301. This is new one. You can try it by yourself. And the BC, okay, is 2423 times this one. I mean, they happen to be the same. But if you want to consider, let's cancel out the C, A should be the same to the matrix B. Unfortunately, you can tell A and the B are totally different. Right? So the cancellation property, okay, is not always true in matrix modifications. But there are some certain cases that this property will apply. But we will talk about that later on. Okay. And then we have identity matrix. Okay. What is identity matrix? Okay. Identity matrix, okay, is always square. In other words, identity matrix always has the same number of columns and number of rows. In an identity matrix, every element are 0 except the diagonal ones. The diagonal elements are 1, and all the other elements are 0. So that will be our identity matrix. Okay. So because of this special shape, okay, the identity matrix, when you modify, okay, to any other matrix, as long as the size matches, obvious, okay, the other matrix stays the same. Okay, no matter you multiply A to the IN, okay, will be A, or IN times A will be A. Okay, it doesn't change A matrix at all. Okay, so this is a very important matrix that we are going to repeatedly mention in this class. Okay. We will talk more about identity matrices later on. Okay, but before that, let's cover one. You could say it's the last important operation for matrix. It's like if A is an n times n matrix, okay, we can do a transpose for this matrix. The transpose basically just like we switch the row into columns. Okay, so if we have every row that looks like it, then after the transpose, which is denoted as AP, this T is denoted as transpose. And you can see every row becomes columns. And as a result, the size of the matrix also changed because originally it's n times n. Now it becomes n times n. Okay? There are some special places that this transpose is very useful. Okay? So again, for the transpose, there are also some associated properties. For example, like if you transpose a matrix twice, it go back to itself. This should be given, right? Okay, basically you change the row into column. Okay, and then, or you can say you change the column into row, right? I mean, basically, like it doesn't. It is the same. Okay, how you phrase the transpose. And then if you do it again, obviously it go back to original matrix. Okay, and A plus B transpose will equal to A transpose plus B transpose, and C the C times A transpose will be C times the transpose of A, and A B transpose will be B transpose times A transpose. This one, only this one is a little bit special, right? All the others are pretty easy to understand. Okay, I'm not saying you should, you know, for a property that's easy to understand, I still suggest you try to prove it formally, because this prove like a theory. Okay, you need to learn, okay, how to prove things. Okay, I you know, I learned a lot of things by intuition, okay, when I was young. So in college, you know, when I was like in mathematics department, my professor always like bring me like I'm not very good at proving stuff. Okay, I guess it's just because like I rely too much on intuition. But so I would suggest you, you know, even for some problem that looks, you know, easy, try to prove it. Try to use like a formal way to prove it. Okay, and then let's talk about the last one, because the last one is like a little bit special. Okay, so here we want to prove AB transpose equal to B transpose times A transpose. So again, okay, AB transpose. If A is n times P, B is P times n. Okay, let's assume A is n times P, B is P times n. Then A times B will be n times n, right? The size. That's first. We have to check if the size matches, right? So the first one results in n times n. How about the second one? B is n, and then we do a transpose. So it becomes like size n times n, right? N times n. And the second one, okay, on the right hand side, B transpose, it becomes what? It becomes, original is P times n, right? Now it's n times P. And A transpose is original, A is size n times P, become P times n, right? So n times P multiplied by the matrix of the size P times n. So the result, it will be the size n times n. So both sides, the size matches. Okay, no problem. So now we are in a position to check if every element match or not. Okay. So let's look at the AB transpose IJ to see that it is the same as B transpose A transpose IJ. So AB transpose IJ, according to the definition, it's going to be ABJI, right? Because we change the row in the column, right? So the index gets switched, right? Index gets switched. And once we switch index, I mean, it's going to be this one, right? AJK times BKI, okay, and we run this K, you know, from 1 to whatever, right? Right? And then, okay, this one, okay, the AJK happen to be like how should I say, can switch. You can switch on. Okay, we consider BKI first. BKI first. Okay, it's like the transpose of B, the M and IK, right? Because it's KI, so it's the B transpose and IK. Same thing, AKJ is the A transpose KJ. Okay, so this one is IKKJ, right? So it's this E transpose times A transpose IJ, right? According to the matrix multiplication definition. So you can see every step along this derivation, we apply the definition. Okay, from the first one, from this one to here is a transpose definition. From this one to this one, it's a multiplication property. And then from this one to this one, basically, again, it's a transpose property. And then from here to here is a multiplication property. Multiplication definition, sorry. So you get an idea. Okay. So this will be an interesting exercise. Okay. If A is a matrix, prove that A transpose is symmetric. What is it? What do we mean by a matrix symmetric? A matrix is symmetric if only Aij equal to Abi for every I and J. Okay, here's the example. Okay, A is this one, and the A transpose is this one, obvious. Okay, the column becomes row, right? And then if we multiply these two, this is what you get. It's a 3 by 3. Okay, and regardless, you can see that this matrix is symmetric. Now, like if you use like the diagonal elements as like a mirror, you can see like the elements, match, from the lower left to upper right. Okay, so this is what we call a matrix is symmetric. So can you prove AA transpose is always symmetric? Okay, I leave this one to you. Okay, I mean, so a small exercise for you, like during the break. Okay, let's take 10 minutes break. We'll come back and we'll continue with the discussion about this. And also, don't forget, we have the exam, right? We have the, not exam, quiz. The first quiz is going to be given, at around like 11:30 today. Okay, so if you have some classmates, they are good friends of you, okay, maybe it will be a good time to remind them, okay, to come to the class if they are not here. Okay, if they are not your good friend, I mean,